Hello and welcome to SETI Live. We are here on a somewhat lovely California day, and my name is Beth Johnson. And with me today, I'm talking to several members of the DART mission, which is the Double Asteroid Redirection Test. So I'm really excited to talk to these guys. I hope you are too. Let us know where you're watching from, and we will give you some shout outs in the chat. And if you are so inclined to reward us for our wonderful outreach with your donations, we will also cheer that as well. So don't forget that your bits, your subs, your stars, and your super chats all go to support our education and outreach programs like this one. All right, with me today are three of our scientists who are working on the DART mission. We have Michael Busch. Make sure you unmute yourselves. You've all been muted. We have Matija Cuk. Hello.
Hello.
And we have Gal Sarid.
Hello.
Hello. Welcome, guys. I'm so glad you're all here. All right. Let's talk about this mission. Michael, what is the DART mission?
So DART stands for Double Asteroid Redirection Test, for anybody who is not aware of NASA's propensity for somewhat contrived acronyms. The idea here is to demonstrate asteroid deflection. So we understand that asteroids sometimes hit the Earth. The idea here is to demonstrate at least one technique to make sure that if we ever find one that is going to hit, we can make it not hit. So DART is going to an asteroid binary called primary asteroid is called Didymos, and the smaller one is called the Dimorphos. It sometimes gets called the Didymoon. Officially,
I will continue to refer to it as Didymon from here until the end of time. Like it's just that's how it's going to be.
So Didymos and Dimorphos cannot impact the Earth. They are not able to come close to the Earth on their current orbits. They actually get pushed very slightly further away by DART. But the primary goal of DART is not to hit Dimorphos. It is to hit Didymos. So not hit Didymos, it is to hit Dimorphos. To get this backwards again. This is not actually the shapes of the two asteroids. This is a different binary asteroid called Mashup. I just happen to have the orrery. It is convenient. 3D printing is fun. So DART will come in and hit the side of Dimorphos as it orbits around Didymos. And the idea is that it will slow it down very slightly, decrease its orbital period, and measure the change in the orbital period of the satellite going around from the Earth, and you can measure the amount of momentum you've transferred into the object. There's a science motivation here too, as well as demonstrating the technology of hitting things in space. We don't know how rubble pile asteroids like these two will react to getting run into by a spacecraft. Material's going to get blown off, how much gets blown off, distribution of the ejecta. We don't know exactly what that will do. Asteroid geology is at the level of hit the thing with a hammer and see what happens. So there is science here as well as the impact hazard motivation.
So Michael, what is your role on the DART mission? What are you working on?
So I am just a collaborator with the mission team. I have not been involved with doing anything with the spacecraft itself. I have been doing some exploration of ideas for ground-based observations after the impact. DART itself is running into the asteroid at 6.5 kilometers per second, roughly 520 meters per second. I forget the exact number. It will be destroyed. It's not going to get vaporized. It's going to get rendered into teeny tiny pieces. There is a small CubeSat provided by the Italian Space Agency that will be way off to the side, and it will take a series of pictures. But to measure the change in the orbit, you have to observe from the ground afterwards.
Mm-hmm.
Shantanu Naidu at the Jet Propulsion Laboratory in Pasadena has led the radar observations of Dimorphos and Didymos and lead the observations after the impact, measure the change in the orbit that way. Other people will be observing with optical infrared telescopes. I've been exploring some options for millimeter observations using the ALMA array in Chile. We'll see what we get. Everybody will be taking any telescope they can get time to look at the impact and immediately what happens afterwards.
Fabulous. And Matija, what are you working on?
Well, I'm a theorist, so I work on binary asteroids. I have worked for a while on how these things form, and I find them endlessly fascinating. In You know, the picture that, well, the model that Nike showed kind of represents a very numerous class of binary asteroids. That the central body looks like a top with a ridge on the equator, and the secondary goes around it. The moon goes around it, and we think the moon is put together from rubble that came off the bigger body as it was spinning too fast. And there is so much physics going on there, and I've been working that for a long time. So I'm looking forward to see how this pile of rubble, what we think is pile of rubble, behaves when it's hit by a spacecraft. And I'll just add that using a binary asteroid is kind of a shortcut here, because we want to stop asteroids as they go around the sun and nudge them away from Earth. But as asteroids go around the sun, their speed is 30 kilometers per second. That's really, well, fast, just like Earth. And if you hit them with a small spacecraft, you won't notice anything for a long time. So we are going to a binary asteroid where there is a much smaller scale, the orbiter is much smaller, and the velocities are much lower. Really, you can outwalk Dimorphos as it goes around Didymos very easily. So if you give it a kick with a 500 kilo spacecraft, I think it's about that big, the difference in its orbital period will be more noticeable, and we'll be able to see how much it moved. And that's the crucial question that the mission is trying to accomplish, because if there are two billiard balls, we know how much you would move the bigger body. But given that it's made of rubble, it's possible that you get the extra kick from rubble flying the other way. But we want to see how it works.
That makes sense. Gal, what is your role?
So same as Matija and Michael, I'm a collaborator on the investigation team for DART. And I collaborate in two different working groups. One is dynamics and one is the ejecta. And to not, restate what my two colleagues just said, I think there are two very basic things that we're interested in, at least I'm interested in terms of this binary asteroid system. One is, what can we tell from what we see post-impact or just after the impact about the transfer of momentum and the actual little pinch of motion that that this whole exercise gives the asteroid. And the other is to understand what these asteroids, and this is an S-type asteroid, one of the most common types of asteroids in the main belt and in the near-Earth object population. We kind of want to figure out what it's made of and what does its surface and subsurface layers look like. And because we can't drill into it, none of us have the Armageddon style equipment, but we can poke a hole and look at the ejecta and how these little bits fly around and behave and try and figure out what were the internal conditions of this object. So that's kind of where I come in and where my interests lay.
Okay, well, I want to give some shout outs here really quickly. So thank you to people watching from, what do we got? Wow, Florida, England, the Azores, Tennessee, Turkey, Belgium, Brazil, Kentucky, Virginia, Scotland, Switzerland, Canada, Arizona, and Georgia. And thank you to Broken Symmetry over on Twitch for the bits. Very appreciated. So Gal, one of the projects that I worked on was cataloging rocks, and so many rocks and more rocks on Bennu. I know that when the tag SAM happened, that sort of went a little more differently than expected because of Bennu being a rubble pile. Has that changed what we expect to happen here with Dimorphos?
So what it did is it sort of gave us a sort of reference point to what small rubble pile asteroids would look like just on the surface, the sizes of these little bits that they have on the surface and their distribution. In general, we just don't know what every surface of asteroid would look like. So in terms of modeling or theory, in terms of what the working group of scientists contributes to the mission, we try and give that kind of modeling background against which the results, the measurements of the actual spacecraft could be either validated or disproven. And that would help us kind of move along in our understanding of both that impact process and the nature of the asteroid itself. So Bennu gives a very, Bennu and Ryugu, the target of the Japanese mission, give us a very clear reference points to what small rubble pile asteroids would look like, and kind of a way to anchor our models into something.
Matija, how common are these binary asteroids?
About 15% of asteroids flying by Earth are binary. And we also think that when you go elsewhere, about the same amount of asteroids are binary. It's not very clear because this behavior is most common in 1 kilometer asteroids. Like the bigger part is 1 kilometer. So, we can't see those very far from Earth, but there seems to be universal processes that make the central body spin up too fast and probably eject rubble that makes a secondary. And right now, the good candidate is for radiation forces. That is like the back reaction from the radiation emitted by the asteroid, just the heat is spinning it up. And sometimes they spin up too much, and then they can't hold on to material. So it's a very universal process.
So these rubble pile asteroids, Michael, can you explain what makes them a rubble pile asteroid? What does that description actually mean?
So we have some larger main belt asteroids. We look at them and they are fairly obviously cohesive. They've been sitting there for 4.5 billion years. Ceres, Vesta, that kind of thing. If you look at smaller objects, though, below maybe, what is the limit, Matija? 80 kilometers or so, they start getting really irregular in size, and they follow this distribution of, they look like pieces of debris from previous asteroid collisions. So this idea of a collisional lifetime stuff in the asteroid belt only lasts so long. All the smaller stuff that we see now is a lot younger than the solar system, and it's reaccumulated debris of previous asteroid collisions. So it's all been broken up into bits and reaccumulated itself. We see this on Bennu and Ryugu, targets of previous spacecraft missions, where you've got mostly carbonaceous asteroid material, but mixed in there is some of the other types of asteroid material, processed basalt from a Vesta-like thing, silicate material like we see on Dimorphos. So these things are all mixed up to some degree, and we're just looking at complicated aggregates of the entire histories of these objects. This raises a problem, actually, which is if we hit one object, is it actually representative of all the other objects? You mentioned Bennu and Ryugu, Gal, but if we look at those, the density on those is about 1 gram per cubic centimeter. So the rock is 50% empty space. You look at Dimorphos, we don't actually know the density of Dimorphos. We know the density of Didymos, and it's about 2. It's twice as dense. Part of that is it's denser rocks, but I don't know how the porosity is different. Should go look.
So there's a lot of unknown going on here. That's interesting. So there's a lot of science that can come out of this. One of the big things, of course, is that it's a technology demonstration to talk about planetary defense and protecting Earth from being wiped, protecting humanity from being wiped out like dinosaurs, right? They didn't have a meteor protection sort of system going on. So how, I know we kind of talked a little bit about this is sort of a shortcut to analyzing how this would work. What is our expectation here? What is our hope? Gal, what are we looking at to have happen here?
So essentially what we're looking is a one point of ground truth to see what happens when we nudge an object in space. We have our numerical models. We have our laboratory experiments. Some lab experiments are large. You can take 2 large balls of cement and have them smack into each other. The problem is that we can't recreate the conditions of space in a lab, and we cannot run our numerical models to get, as close a result as possible if we can't anchor them in observations and measurements in the lab. So our hope here is that my esteemed observer colleagues would be able to pinpoint the actual change in the orbital velocity of Dimorphos in the binary system. Maybe if there are any shape effects or spin effects due to the introduction of the momentum into the system. All of that will tell us eventually how we can scale our experiments and our numerical models to deal with, the thing that kills the asteroid when it comes, when it comes for us. So that's sort of the overall goal.
All right. I want to give a quick shout out to some more viewers from, it looks like Texas, Wisconsin, Greece, and Utah. Wow, we were all global today. All right. I'm going to look at some of these audience questions that we have coming in. So I do see that you guys are asking questions. So feel free to share those in the chat and we will pass them on. Michael, how many people work on the DART team and how long has this project been in planning?
You're asking me this one?
Yeah.
So it's a couple of hundred people on the DART mission team, if you count all the investigation team and all of the engineers, but there's many, many more people who have been involved in various capacities. It's built a whole spacecraft out of parts from many different companies, many different research agencies. We have contributions from Italy, we have contributions from various labs in the United States, and it's been put together under pretty difficult circumstances. They had to modify a bunch of the procedures at the labs when they're putting it together, so because the pandemic is happening. Fortunately, it's put together in a clean room and everybody's wearing masks and gowns and everything's getting filtered anyway. But it still was very rough conditions for the engineers in some parts of all of this. And then it was driven across the continent and stuck on a rocket in Southern California and launched into the sky a couple of weeks ago, which involved even more people.
So
I'm
a
not sure
lot
you
of
can even
people.
do the full accounting of everybody who's been involved in this. Different versions of the mission I've seen proposed over about 10 years now. It was 4 or 5 years ago now that the mission was approved in the current form.
And okay, we're hitting a rock. We're hoping it moves. Matija, how much are we hoping it moves by? Will it affect any other asteroids? Michael has stated it's not a threat to Earth. I'm sure that's the case, but what are we talking about here? What kind of movement are we expecting? Are we hoping to get out of Dimorphos?
Well, its orbital period around the central body is on the order of a day, and I think, if I remember correctly, we're hoping to change it by a few minutes. Was it 10 minutes or something?
73 seconds, I think, is the minimum threshold.
To measure.
An annoyingly precise number, but that's the minimum. Presumably, it'll be higher than that.
Yes. So we would have never noticed. First, you can't see this thing from Earth without a telescope. And the one thing about these small binary asteroids and small asteroids in general is that this is not the eternal music of the sphere. These things bump into each other all the time. They evolve on much shorter timescales than people usually think about space. So periodically, there must be exchanges of boulders and other junk between Dimorphos and Didymos. This is, in the grand scheme of things, this is not something that doesn't happen in nature. The difference is that this is now controlled. We know exactly how big the spacecraft is and how fast it's kicking Dimorphos. And then I'll just add one other thing, is that while this is a test and it's a bit of a shortcut in terms of velocity of the asteroid we are looking at, because we're looking at a satellite of an asteroid that's moving slowly, so we can test a much smaller spacecraft. This is kind of, in terms of size, the asteroid we might be having to deal with, because, you know, the dinosaurs were really unlucky to have a really big one coming up, but those are rare. The first one that we might have to deal with is not going to be that big. It might be about 100 meters or more across. And, you know, that doesn't sound, you know, it's 100 times smaller than the one that kills dinosaurs. So what's the problem? Well, what happened in Chelyabinsk a few years ago was way below the threshold. Like the whole city was quite rattled, and it was a half a megaton event. So so in terms of size of the target, this is actually what might be realistic, if not the velocity of the target.
And part of the reason that Chelyabinsk wasn't more damaging was because it sort of skimmed the atmosphere rather than coming straight through. So you didn't actually have an impact event, a huge impact event, correct?
Things this small usually don't make it to the ground anyway. And actually, even the one that we have to worry about, say 100 meter body, size of the Didymos, just single, coming straight at us, it can do damage without actually making a crater. It would just be like a airburst, and can be, you know, Pretty, we're talking about 100 megatons or something. That's horrible.
Is this on the scale of Tunguska?
I asked Michael about that.
Peter Uniskins is our best expert at the Institute on Tunguska, but he's not here today. That was a couple megatons to tens of megatons, the Tunguska impact in 1908. And that, again, didn't make a crater. That just flattened an area the size of the city.
I think it was on the order of about 10 meters, Tunguska.
That was Chelyabinsk. Tunguska was bigger than that.
Bigger than that, yeah.
It was a couple tens of meters.
But it was about 10 megaton. And something that's more than 100 meters across is going to be hundreds of megatons. So really serious.
Now, just to emphasize for the audience here, the impact rate of something like Tunguska is once every couple hundred years. The impact rate of something 100 meters wide is maybe per few thousand years.
Right.
Survey programs are designed to find everything in the 100-meter size range and up with decades of notice. Eventually, it will take time to do that. We can say there's nothing that kilometer-wide that's going to hit anytime soon. There's other surveys that are designed to find the small things with shorter notice, but we don't talk about deflecting those because usually it's out over the ocean and it doesn't cause a problem.
Okay. So what you're saying is nobody has to stay awake at night worrying that we're going to get hit by a massive asteroid anytime in the near future.
There is one 1 kilometer wide asteroid with a possible Earth impact that we haven't quite ruled out. It is in 860 years.
Oh,
we'll probably rule it out before that.
All right. This isn't going to cause me sleepless nights. So, you guys talked a little bit about how we're going to need to do some ground observations of any changes to Dimorphos's orbit. Is it possible for any citizen scientists to do that? Can this sort of thing be observed with a home telescope? Anybody? Gal, maybe?
In principle, I would defer to Michael, but I think home amateur telescopes probably are a bit too small to get anything out of it, because even if we consider a lot of ejecta coming out, it's still going to be pretty small kind of projected surface area that reflects light back to Earth. Mm-hmm. So from the ejecta model they've seen, I don't think it will, create like a large flash for an amateur level telescope to be able to observe it. I do know there's a lot of telescopes around the world that are aimed at it. I think down to maybe a 1 meter aperture, but I might be off here.
So I was actually on a conversation this morning where this came up. The various professional observatories that will be doing ground-based follow-up are not planning to see the actual flash from the impact.
Right.
Because that's over very, very quickly. The Matija CubeSat that's flying by only a few hundred kilometers out, it will see the flash and image the ejecta plume in great detail. From the ground, professional observatories should be able to see the ejecta coming off. There's questions of if there's some water that gets puffed into vapor, maybe that will show up, but that again is not something you're going to pick up with a backyard telescope. Usually you don't have a spectrometer on there. Their main follow-up observation from the ground to figure out the change in the orbit is just a question of timing. So if you can do a light curve observation, see how bright this is and how bright this is put together, you see it go up and down as the thing spins around. Mm-hmm. People do that with backyard telescopes, but it's a little bit more involved than just sticking your eye to the eyepiece. You put it into the computer, you carefully calibrate the brightness measurements off of background stars, and you can see the light curve go up and down. And when it goes up and when it goes down will change by a few minutes from the impact. Mm. There's one point where you might be able to see it just without all the complicated details, which is timing when the satellite goes behind the primary. We call this a mutual event. But those only happen at very specific times when the Earth is passing through the equator. And that won't be the case right at the time of the impact. So unless you've got the high-end gear that some amateur astronomers do have, but not many, it's not going to be seen from a personal telescope.
Okay. quick
As
thank
Matija
you
said,
to
normally you won't notice.
quick thank you to Ron on the Bayou for giving us some stars. Thank you very much. I do have an audience question here. If we discovered a threatening asteroid that was heading for Earth, how far in the future, how much time do we need to intercept it with something like this? Are we talking months? Or are we talking years? Michael?
So I mentioned earlier, DART has been being built over the past few years. The mission got approved 5-6 years ago. It took a couple of years to build the spacecraft once they had all the engineering in order. So a couple of years is the minimum time to build the thing. But you're set by when you can launch. DART had to launch at an exact second on each day starting around Thanksgiving in order to get out to the right spot such that its orbit around the sun intersects with the asteroid's orbit around the sun.
Right.
So you have to have a launch window set up for that. That only happens every few years. The orbits have to be syncing up. So you will want many years of warning to do an asteroid deflection. Some people who work over at the Livermore National Labs on the other side of the bay talk about retasking nuclear weaponry to move asteroids with zero notice, and I don't really care to think about that too much. I just try to have as much advance notice as possible.
Fair enough. That sounds
Which
reasonable.
is why I'm talking about the earlier case, the radar observations of a particular asteroid with possible impact 800 years from now. Just measure the orbits as well as we can and run them out as far in the future as possible. And then I hand off to dynamicists like Matija to figure out exactly what's going to happen with them, because I'm used to looking at them on the sky and not doing the math for where they're going to be.
Matija,
I will just want to add that while all this is true, we can use lessons from DART to shorten that time scale a bit. We can have the technology ready, be it off the shelf or ready to go spacecraft, or even spacecraft in orbit ready to intercept, so that we can at least minimize the time it takes to build the thing and launch it. And
I must disagree with you. Keep the spacecraft in orbit, because keeping a spacecraft in orbit on working order is hard. There's the Comet Interceptor mission from ESA, which is doing lots of work to try to guarantee that they can stay out there until a comet comes by that they can get to. But you have the technology now. You know how to build the spacecraft, so you can build it faster the second time. This is true.
Matija, what are you most looking forward to about this mission?
Well, I want to see a binary asteroid up close. Later, in a few years, there'll be other missions that will look at other binary asteroids similar to Didymos, and fortunately, we'll not mess with them. Just take a picture of them as they are and in nature. But even before, before the impact, we'll see how this thing looks like, because I've been working on this for a long time and never seen one up close. And then I want to see what happens when you hit the moon. We have all these ideas that what's inside and how it behaves, and it's, as dynamics goes, it's a very interesting object in the gravity field of the primary, regular shape, and so on. And it's kind of a primitive experiment. You hit it and see what happens. So we'll see what happens. And I would add, just for the kinetic impactor technique, which is what DART is testing, you want to have decades. And if you're lucky, you might have centuries. And that's kind of a realistic time frame once we have enough coverage from both space missions and ground-based missions of the asteroids in the desired range.
Gal, what are you most looking forward to?
The boom. I'm really happy that the Italian contribution of Matija Cuk came into DART. I'm really looking forward to the last few images of the Draco imager before the spacecraft hits the surface. I'm really looking forward to see what Matija Cuk is able to image from the event itself and get it back to us. Because as I said, no matter how much we model and do experiments on Earth, we can't recreate the right conditions for something like this in space. And in a word, it's really cool to hit something in space and see what happens.
Michael, how about you? What are you looking forward to?
So there are some very peculiar possibilities that may happen depending on exactly what goes on when DART hits Dimorphos. So we have the asteroid out there. I have props, I'll use them. So the basic idea is you hit it straight along the direction of its motion, actually opposite. It's rotating this way and you hit this way. And you slow it down a little bit. But it's not going to come in straight like that. It's coming in at an angle off down like this. It probably won't hit the exact center of the satellite. So what happens there? We may make the satellite tumble. We may make it get on some complicated eccentric inclined orbit. Some very complicated dynamics may result from this. That'll look really funny from looking at the light curve and the radar observations from the ground. And again, I'll have to hand up to the dynamicists as to what's going on exactly there, but it'll be interesting to look at.
That sounds exciting. Actually, I'm kind of excited for that part too. So is there anything else you guys want to tell us about this mission that you haven't had a chance to tell us?
Well, there is a bit of a kind of curiosity, which is my first time I'm working with something that's in planetary defense. So for example, we are all collaborators on the investigation team because it's not a science mission. So it's not called a science team. You know, every NASA mission has a science team because they are part of the science mission directorate, but this is separate. So it's kind of interesting to be in a different department, and just the word science is not used as much as possible because it's not what it is about. It's about defense.
There is one point I would like to mention, which is that DART and Matija Cuk are not the only spacecraft going to Didymos and Dimorphos. The European Space Agency is doing a mission called HERA, which is to launch in 2026. I am forgetting now. Shameful that I am forgetting because I've been so focused on DART. But HERA is going forward. It will go out to Didymos and Dimorphos. It will actually go into orbit around the asteroids. And this is a very complicated formation flying problem now because there's a moon there and there's the main asteroid there, and neither of them are around. But they will orbit around as best they can. And they will also land in a couple of small satellites onto the surfaces here and try to do deep radar sounding, see what happened to the inside of Dimorphos at the impact. And that will give us a whole lot more information as to what the interior structures of these orbital piles are like. HERA is the latest iteration of a few different mission proposals that have been made to ESA over the past more than 10 years now, which finally going forwards in collaboration with DART. So together they form the AIDA project, which I forget what that acronym is supposed to be, but it emphasized the international collaboration here.
Okay.
And we've got many different groups of people working on different parts of this problem.
It's such an interesting and incredible mission to me. I'm really kind of invested in this one to see where all of this turns out. So we've kind of reached the end of our time. So thank you, gentlemen, for joining me and talking about this mission. And I'm glad that SETI Institute has so many people working on the investigative side of it. We'll not mention that S word. Planetary defense, of course, is incredibly important, especially when we talk about asteroids coming for us and not wanting to take the kind of damage we've taken in the past. So thank you for all of your hard work on this, obviously, and for participating in such a big collaboration. Thank you to our viewers for watching. Much appreciated that you are all here. This is not our last SETI Live for the year. That will be on Tuesday. I will be speaking with Seth Shostak and Natalie Cabral about astrobiology and our hopes for SETI in the coming year. So join us then. And as always, we are a nonprofit organization. So all of your donations, your bits, your subs, your stars, and your super chats all help us put together our education and outreach programs and keep bringing you all of this fantastic information so that you get sort of a front row seat to these missions. Hopefully we will have these guys back when we have some science results. The impact is scheduled for September of 2022. So you're gonna have to wait a little while, but we will be back with more on DART later in 2022. So thank you everybody for joining us and have a lovely rest of the week.
Thank you.
Thank you, everyone.